Hi everyone, and welcome to this video lecture on the free vibrations of single degree of freedom systems. As I have shown you in the experiment with the cart on the rails, if we subject a single degree of freedom system to initial conditions, it will start to vibrate. And I would like to start off this lecture by asking the question, what does the frequency of the vibration depend on? I will denote the frequency of vibration by omega n, and that is also called the natural frequency. Natural frequency. And it's called natural because it is the frequency in which the system vibrates if there are no external forces acting on the system. So what does it depend on? We will try to discover this by means of dimension analysis. Dimension analysis, which is a very powerful tool. So let's have a look at the dimensions of omega n first. Omega n is measured in radians per second. All right, but since radians are dimensionless, they are meters per meters. These are 1/seconds. Well, what parameters could it depend on? Well, it could depend on the spring stiffness. And the units of spring stiffness are Newton per meter. Okay, in standard units, this would be a Newton is a kilogram meter per second squared times 1/meter. So the units, the dimensions of K is kilogram per second squared. Okay, and finally we have the mass of the system, and that is just in kilograms. All right, so if we are wondering what does the natural frequency depend on, we can try to construct 1/seconds using K and M. And you can see that if we take the square root of K over M, that this is indeed has the units of 1/second. Try this for yourself. So that means that we know that this natural frequency should be something with, it should be proportional to the square root of K over M. Taking the square root of K over M is the only way in which we get the correct units 1/seconds. So it can still depend on some numbers. It can be like 2K over 3M, or it can be pi times the square root of K over M. So there can be a linear scaling of these parameters, but it should be something like this. And what it exactly is, that follows from the analysis. But at least we know it will be something with the square root of K over M. Now, the next question I would like to raise is what we saw in the experiment is that this vibration slowly damps out. And one could wonder if the damping has an influence on omega n, on the frequency. So suppose we consider the damped scenario. So I draw this spring damper system now with K, M, and damping coefficient D. Let's suppose that this is the case. So suppose that we have omega D, which is the frequency of the damped vibration. Maybe it's the same as omega n, maybe it's not. Let's try to find out. Well, its units are of course also 1/second, right? Because it's still a frequency. So that means that we can only realize this if omega D is something with omega n, which has already the correct units, times some function f, which is dimensionless. Okay, so there can only be dimensionless arguments. because omega n has already the units of frequency, it can only work if we have omega d as omega n times something that is dimensionless. So let's see if we can construct something dimensionless from k, m, and d that includes d. So let's have a look at the units again. So k was in a Newton per meter, and we discovered that that was equal to kilograms per second squared. The mass was in kilograms, and the damping coefficient d, the units of it are newtons seconds per meter. All right, so newtons are again kilos meters second squared, and then times second over meters. So this is kilos per second. Now, if you study this properly, you will find out that the only way to construct something dimensionless from this is when we have d divided by k over m. This is dimensionless. All right, so that means that if damping has an influence on the frequency, it will be some function of this d divided by the square root of k and m. All right, so let me write that down to conclude. So omega d must be something with omega n times some function that we do not know yet times d divided by the square root of k times m. All right, and well, we will see later on if this function actually exists, what is this relation exactly. But I think this already gives you a heads up on what the solution will look like, what this frequency will look like. So let's now try to actually solve the equation of motion. So let me write down the equation of motion again. We had mass times acceleration plus damping coefficient times velocity, stiffness times displacement is equal to 0. And the system is subjected to initial conditions. x0 is x0 and x dot at 0 is x dot 0. Good. Well, in order to derive the solution, we use the methods for second order homogeneous ODEs. I will start by rewriting this equation such that the term in front of the x double dot is 1, like this, k over m times x. And now I will introduce two parameters as follows. This d over m, I will call that 2 zeta omega n times x dot. And k over m, I will call that omega n squared times x is equal to 0. The reason that I do this is because I already know what the solution looks like, and the solution is much more convenient in terms of these parameters. So in this I have now defined omega n as the square root of k over m. So there it is again. And I have defined zeta as d divided by 2 m omega n. And if you rewrite this, this is d times 2 times the square root of k over m. Okay, so the way I have introduced these parameters looks very, very close to the parameters we encountered in the dimension analysis before. This omega n, it turns out that omega n is not just something with the square root of k over m, it is the square root of k over m. So this is the natural frequency. And these zeta, so we see that we have this factor d divided by the square root of k over m, of which we know that is dimensionless, now just divided by a factor of 2. And the factor of 2 is just an arbitrary number that makes the expression in the end look nice. And this is called the damping factor. Damping factor, which is a dimensionless number, a dimensionless measure for the amount of damping in the system. Okay, now let's try for solving this an e power. That is the standard procedure, e to the power st. We substitute it, and then for the second derivative we get s squared. Then we have 2 zeta omega n times s plus omega n squared e to the power st equal to 0. So since e to the power st is never 0 for finite values of s and t, it must hold that s squared plus 2 zeta omega ns plus omega n squared is equal to 0. And this is called the characteristic equation. Characteristic equation. Good. So this equation can be solved using the quadratic formula. It has two roots, s1 and 2, so it's minus a half times the second term, so that is minus zeta omega n, plus or minus a half times the square root of the second term squared, so that is 4 zeta squared omega n squared, minus 4 times the third term omega n squared. Looks like this. Let me slightly rewrite this. S12 can be written as a minus zeta omega n, plus or minus, well, this half cancels the 4, and I can take omega n squared outside of the square root. So it looks like this, omega n times the square root of zeta squared minus 1. So these are the solutions from the characteristic equations. Characteristic equation, S1 and S2 look like this. So we managed to solve this characteristic equation, and that means that the general solution for free vibrations is as follows, that x as a function of t is c1 e to the power s1t plus c2 e to the power s2t, where s1 and s2 are as defined above, and c1 and c2 are arbitrary coefficients that depend on the initial conditions. So if you know the values for zeta and omega, you can substitute it in s1 and s2. And then by applying the initial conditions, you are able to determine C1 and C2. All right. So with the establishment of this general solution and the roots S1 and S2, in principle, we have solved mathematically for the free vibrations. However, it is very nice to give some more physical explanation to this mathematical solution. I will show you some examples that depending on the amount of damping, so depending on the value of zeta, the behavior is different. All right, and that I will postpone to the next video. So keep watching if you want to find out what this solution looks like for various values of zeta. Thanks for now.